Welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse, and with me, as usual, is
Robert Moore.
Robert. This is our 32nd episode.
Hard to believe. Seems like we just started yesterday, but it's been almost a year, hasn't it?
Well, we actually gone into another season now.
Yeah.
Transitioned into fall from
Into
summer.
fall. Yeah.
So, what do we define the beginning of fall for us in the Northern Hemisphere? Robert, do you remember astronomically speaking?
I do. That would be the equinox, so the autumnal equinox, I suppose I should say, as opposed to the vernal equinox. So that happened on the 23rd, early in the morning, as I recall.
Yeah, it'd be early Saturday morning for us.
For us, yeah.
Yeah, so where's the sun relative to the celestial sphere at that point?
You know,
Put you on the spot today?
it's right on the celestial equator.
There, that's all I wanted to
much.
know.
Okay.
Okay, so it's right on the celestial equator. That's the thing, right? Heading southward.
Setting southward.
Yeah, and so we will cheer 6 months from now when it's on the celestial equator heading northward, and that's what gives us our summer here in the Northern Hemisphere. Of course, everybody in the Southern Hemisphere is cheering because summer is spring and then heading into summer down there.
Right.
Yeah, so that's always a good time, when spring begins around here, especially where we're located, right? We can have a long winter with a lot of snow, and it may not be the first day of spring when that snow starts melting, but it's shortly thereafter, right?
Yep.
Around here. So.
Well, this past winter was kind of unusual. It got into April and it was still snowing. So
yeah, and even when the days get longer, you can kind of get that feeling that things are turning around to winter weather, right? Coming out of the darkness of the winter in that sense, which really means, like late December or January is probably the worst time.
Oh, yeah.
Unless you're love the winter season, right?
I do. So. I love the winter season, but at the same time, it's like when it starts dragging on and on and on, it's like, nope, we're done.
Yeah.
Bring on some warmer weather.
Now, this week we're not having a special guest. Next week we will.
Mm-hmm.
And we have a couple coming up, hopefully, and several different podcasts in a row here. So it's just you and I this time, Robert.
Just the two of us.
So usually when we do that, we talk about things that are happening in the news, astronomically speaking. And there was sort of a major event that happened on the weekend. You want to give a little rundown on what that was?
And that was the return of the mission OSIRIS-REx, which dropped off a package. It had been to the asteroid Bennu, and had taken a sample from the surface of Bennu and brought it back to Earth. And that dropped in New Mexico? No.
Utah. Yeah.
And over the weekend, right?
That's right, yeah. So do you know what Osiris stands for, OSIRIS-REx?
I know Osiris is the god of the underworld in the Egyptian mythos, but I don't know particularly why they picked that name.
So here's what OSIRIS-REx stands for.
Okay.
You ready?
Yeah.
Origins.
Okay.
Spectral interpretation. Resource identification. Security. Regolith explorer. So they didn't start with that. They started with OSIRIS-REx or something. One would think, I'm speculating, and kind of work backwards to see what are all the different things we can put into that.
I've been to two of the Sagan exoplanet conferences. And at all of them, we had to laugh because in our play projects we developed, we made fun of the fact that NASA loves its acronyms.
Right. Well, it's interesting to see the word security in there.
Right.
So can you maybe speculate what that means?
I can, actually. I was surprised to find that out. I thought Bennu was actually a main belt asteroid, but it is an Earth crosser. And it's going to make a close approach the next year or two, I think. And depending on whether it hits a keyhole determines whether it makes a really close approach in 2138.
Okay.
Potentially even smacking the Earth. And people go, what's the big deal? We get, meteorites falling all the time. This asteroid is large enough that it'll strike with enough force to devastate a region the size of Texas.
Right.
So I've done a little poking and found out things like that. It's in the thousands of megatons that will be the energy of the impact. And considering the biggest nuclear bomb we've ever made is like 50 megatons, Yeah, it's a few orders of magnitude larger than our largest bomb.
And of course, anybody who's watching this live, if you have any questions or any comments on what we're talking about or anything else, please feel free to use the chat function.
Right.
And also, we should mention we are broadcasting live from the campus, as opposed to being dead, I guess, from the campus, University of North Dakota here in Grand Forks.
I think it's as opposed to being recorded.
Yeah, exactly. It's always fun to talk the other way.
Okay.
Do you want to show our first slide, Robert? Because that's related to what we're talking about
actually,
here.
we should have done that. So
Yeah.
this is what Bennu looks like from OSIRIS-REx and its imaging cameras. So the right is it approaching and got a pretty good view of the whole surface. And then the left is actually where it was close in on the asteroid.
Well,
No?
No.
Oh, that's Utah.
Yeah, that's Utah. That's the
Utah
capsule. That's
Oh.
the picture taken this weekend.
You see, I'm looking at a big little tiny
Right.
box.
You can see the parachute above it and to the
Yep.
left a little bit.
Looks like red squigglies.
Mm-hmm. So the image on the right is Bennu, as you mentioned. Now, the spacecraft did get there in 2018, and it left in 2020. So it hung around for a couple of years, making various measurements and so on. So it's interesting, we're up to the point of not just flying by these objects and you have like just a few minutes, or if you think of the long approach and the receding, maybe hours or days or months even.
Right.
But we're able to hang on, like orbit the object and station keep with it, stay nearby, and do a lot of detailed analysis over 2 years periods. That reminds me of the one that we had around Ceres. You remember that?
Mm-hmm.
That was the Dawn mission, was it?
The Dawn mission, I think.
Yeah. So that stayed around the vicinity before it decided. NASA decided to move the spacecraft somewhere else.
With Ceres, it's kind of understandable. You can Ceres is large enough that it's actually spherical. So getting into orbit around it isn't as challenging. But something like Bennu, that they got it into orbit just is phenomenal, because the thing has almost no gravity. It's still small enough that you could launch yourself out of orbit and into space by sneezing too hard. So...
Yeah, and so you can wonder about the propulsion system on that spacecraft. Do you want to maybe make a comment about that?
I'm not sure which propulsion, but if it's like any of the recent ones, it's ion propulsion. So it uses a high voltage grid to ionize and accelerate xenon atoms, usually, through the grid and blow them out at very high speeds out of the back end of the spacecraft. This produces thrust that's on the level of like a sheet of paper in your hand. But when you're talking about the distances and time lengths in space, it's very efficient. It just produces very little thrust. So over long time periods, it's a good thing. But, if you want to get there quick, it's still not the best thing in the world.
Well, the thrusters that are on board the spacecraft are all really small. So it has 28 engines in total, which is, they have like a high thrust main engines and some, medium-sized thrust engines, and then some altitude control thrusters.
Okay.
And so they produce, on the order of about 200 newtons each. So a very small amount of force. Yeah. And that's how they can do that fine adjustments. Okay. And they actually use hydrazine. So, so they're not like the type of ion propulsion. So
that I'm used to.
That you're used to, right? It's very sort of very gentle thrusters. Yeah. And it's kind of cool. So what they do is they actually take the hydrazine and flow it over a heated metallic catalyst bed. And that creates a high pressure gas that then expands out through the nozzle of the engine. So it's a different type of process than what we're used to.
Right. I'm used to the hydrazine chemical rocket using an oxidizer to ignite the hydrazine and blow it out.
Yeah.
So this is a different type of rocket than I'm used to hearing about.
And you might think, the ion type of propulsion, they have very low thrust. Mm-hmm. But those are the things you can run for tens of thousands of hours.
Right.
And so you can just keep, and that builds up over time. You're, changing your velocity and stuff, right? To give you enough acceleration. The acceleration acting over a long period of time can really change your velocity after a while. And so you want something probably a little bit more here and now, right? A little bit oomph to it.
A little bit oomph.
And so using these type of thrusters, then they can, because like you mentioned, because of the low mass of this object, it's very difficult to have a really stable orbit around the asteroid.
It is.
And so to have, some thrusters that can do the station keeping, as we would say then, it's something that you have to put a lot of thought into that.
And that's what they're doing. This is why we still need, rocket scientists.
Right.
They're trying to come up with new types of rockets that allow them to work with different scenarios and different situations. Because the ion propulsion I was talking about probably wouldn't have been enough to keep it in orbit around Bennu, whereas this is a nice intermediate level of thrust where it's not rocketing it past, it's just kind of nudging it here and there.
Yeah, so we're so used to the brute force method from the old beginning days of the space program, right? Where you like the engines, you're gone, right?
You're gone.
And usually it's because you're lifting off from the surface of the Earth, and you do need a big impact, something that's going to produce a lot of thrust to get you off the surface. But once you start maneuvering around objects that are not planetary-like in size, like asteroids and so on, or approaching comets, we've done that in the past. You think of the Stardust mission.
Right?
And that you really have to have a really adjustable type of thrusters to do that fine correction that you need to the trajectory or the path of the spacecraft itself. So that's kind of interesting. And like I said, this technology is improving all the time, right? Maybe these things weren't available in the 60s that we could have done that anyways.
Right.
If it would have probably been more bulkier, therefore carry more mass. And in the science of rocketry, the number one goal is to get your thing done, your goal, reach your goal, right? Do the operations you need to perform with the least mass possible in terms of your spacecraft.
This is why we're looking for water on the moon and in other locations, is because that's mass you don't have to lift off of the surface if it's already there.
Yeah, it's very expensive. I remember one of the goals of the space shuttle in its first incarnations, at least it was written a lot about that I read back, in the late 70s, is to try to get a spacecraft that would reduce the cost per pound somewhere, like $1,000 per pound or $100 per pound if it was possible.
Right.
But it didn't work out that way. It came that the shuttle was supposed to, a given shuttle, because there were several of them, but one particular shuttle would land. It would take 2 weeks to turn it around, put it on the launch pad, and then launch the thing. So and if you have that many flights occurring in multiple shuttles, that would reduce the amount of cost per mission, you see,
right.
And therefore reduce the amount of cost per pound of payload that you're carrying to get to these order of magnitudes of maybe $1,000. And if you could really do a really good job, maybe $100. Never worked that way at all.
But that's what SpaceX and Ad Astra and Blue Horizon and other companies are trying to get to, is that they can turn around that quickly.
Well, look at all the launches that you might notice, like the Starlink launches.
Right.
It seems like almost every second or third day there's one going up. So the turnaround is incredible, the number of launches, that they're doing, irregardless of what you think about the payload overall.
Right.
Tens and tens of thousands ultimately of Starlink satellites being put into Earth orbit, low Earth orbit.
Basically making, ground-based observations of the sky nearly impossible because you've got a satellite that zips across the field of view.
Yeah, let's just say it makes it a little bit more challenging. How's that?
Okay.
We're being nice. We're being nice here.
We're being nice, right.
I mean, people do benefit from the Starlink.
They do.
Right? That could be life-saving, right? If you're somewhere where you have otherwise no means of communication,
right,
and you need to contact authorities maybe for medical help, you could save people's lives.
Right. I just wish they were in a little higher orbit so that there could be fewer of them seeing a larger horizon.
Yeah, and you know why they're in low Earth orbit, LEO, as we say?
I don't know the specific, but I can guess at a reason, and it's cheaper to put them there.
Well, and it's tied to the latency factor.
Okay.
If you have them in like geostationary orbit, they're a lot further above the Earth. That extra time, even though you think it's nothing, right? The time difference and the speed of light of the transmission signal. But that stuff is all processed through ground stations.
Got it.
And it's like anything else, what do I actually get? Don't tell me what the specs are.
Right.
Right? I can hook up a new computer, and the computer is supposed to be this fast with this type of CPU and all that. But I want to know, when I'm playing my favorite video or constructing videos, is it going to slow me down, right? Is it
Right.
going to be a hindrance to the operation I want to perform, my objective, right?
And geosync is about 30 seconds of latency, I
It's
think,
less than
something like
that, but the idea is when you
Okay.
when you're typing on a keyboard, you want near instantaneous,
Right.
on your screen. If you're typing, let's say, going through another computer that's on the internet, and you want it to go on your monitor, so you're doing it remotely, right?
Right.
And the latency, even if there's a little bit of a hesitation there, that's enough to make it annoying, should I say?
Yeah.
And so that's
and
one
life
reason.
threatening, which is one of the reasons why they're going up there.
Well, you definitely want the whole world covered by a means of communication, right?
Yeah.
So you remember the old sat phones people would use?
I do. Huge things.
Yeah, and nowadays, even cell phones, you kind of, you say some bad choice words at them because sometimes they're not that reliable. And you're not really
Right.
that far away. You could be just several miles away from the nearest cell tower, and all of a sudden your reception is poor, depending on the train and so on.
Right.
And you would love to have something maybe that you could use anywhere in the world, whether it's on the North Pole, Antarctica, or in the deep forest somewhere, even on the North American continent, that would work reliably. In fact, people argue that the old landlines were actually better in terms of the quality of the sound than people using a cell phone from their home, calling the same location somewhere if two of you are on cell phones.
As long as it was a digital signal, I will agree. But,
Yeah.
When it was old analog systems, I will disagree with anybody saying it was better sound quality.
Well, it was certainly better than two cans in the string, Robert.
Oh, okay. Yeah. Okay. Yeah.
But yeah, so improvement in technology, whether it's an actual improvement or not, I mean, that's something else, right?
Right.
It's like upgrades, right? Is it really an upgrade?
Right.
Yeah, you kind of, or are we just going sideways with this thing, right?
Or are we just doing a lateral promotion? Yeah.
Right, exactly. So it'd be interesting. So this sample landed on the weekend, and it's not the first time we've done this as a human population, species, because the Japanese had brought back the
Hayabusa 1 and 2 both brought back samples.
And NASA brought back a sample from the comet. Is that Velt 2, I think it was?
I think so, yeah.
The Stardust mission, right?
Right.
And that also landed in Utah. Remember it had that aerogel where the particles would come in without being destroyed?
And it crashed instead of being caught.
Right, exactly. But you can do one of these citizen science projects, at least they used to have it geared up, where you can actually look for tracks in the aerogel and help identify potential interstellar medium particles, this kind of stuff, which are raw ingredients, if you like, from which stars and planets form from. So that's kind of interesting from that point of view, right?
I agree. Neat stuff.
Yeah. So, and the other thing that's been in the news lately, of course, is information from the James Webb Space Telescope. And what you're seeing here is images of Europa. So one of the moons around Jupiter.
I will point out one of the Galilean moons. So it's one of the ones that Galileo was able to see with his dinky little telescope.
Now, what were now Galileo saw 4 moons around Jupiter. So Europa is one. Can you name the other 3, Robert?
Ganymede, Callisto, and Io.
That's right. Exactly. Very nice. So that's the 4 largest and therefore more easily observable.
Right. In fact, Ganymede is larger than the planet Mercury.
Yeah. So that makes it easier. In fact, if Jupiter wasn't there and you still had those objects at the same distance, they'd be easily visible.
Right.
Even to the unaided eye in a dark location, you could see the reflected sunlight.
But as dim as Jupiter looks, it glares enough that it actually obscures us being able to see those moons with our eye.
Yeah, in fact, you only need even a small pair of binoculars or even a small telescope, an amateur, really small telescope, would be able to see those moons. In fact, Galileo's telescope, by our standards today, was certainly a very small amateur-type telescope.
It's less than an inch, I think.
Yeah, it was like on the order of 1.5 inches or somewhere in that ballpark, right? So, yeah. And plus it had very poor optics, right? The optics that we make even in a cheap refractor of 2 inches in diameter is way better optics quality of the lens than what Galileo had at his disposal. He essentially made his own in that sense, and it'd be the early 1600s.
1600, right?
So that's when Galileo did his observations of the sky.
Who is the other one that you can also credit with being the first European to turn a telescope to the sky?
Well, I mean, there was
several. I know one in particular who fought Galileo's name being the first, and that was Hans Lippershey.
Yeah, right. He was the actual inventor of the telescope. That was in the late 1500s from the Netherlands.
Right.
Yeah. So Galileo heard about the invention and made telescopes, and one was for profit.
Yes.
Money drives everything, as we say in this world, and it certainly was the case even 400 years ago. Yep. And so Galileo's idea was to make telescopes and sell them to the military like the Navy. And what manage the advantage, right? People are scanning the horizon with their eyes, and yet here comes along a telescope where the Navy that has that device would be able to spot enemy ships approaching long before they could see you, to give you more time to prepare. In fact, you could be even on the land, like at harbor somewhere, right? As seeing the ships coming in, and they don't think that you can see them, but you can with your telescope. And so you have lots of warning to get the cannons ready, to get the gunpowder ready, when all the stuff that you need to get ready for a battle, essentially.
That's it.
So you do have have an advantage in that case.
You're still got a limited horizon, because the curvature of Earth still takes you out of sight. And people don't. So there's some people who don't like admitting this, but it's the masts of the sails that you see first.
And the other thing is, you don't know if it's really friends coming,
right,
or friends who someone who's coming that shows us they're friends because they're waving a friendly flag, but you can clearly see activity on the deck of the ship that they're preparing their cannons.
Right.
You see, there's an advantage right there. Maybe not so friendly.
Maybe not.
Yeah. So anyways,
what's going on with Europa?
Yeah. So getting back to Europa. So what was in the news lately is the detection of carbon, mainly in the form of carbon dioxide, coming off of Europa, which was spotted by the James Webb Space Telescope. Now, Europa is one of these satellites of Jupiter that we have lots of detailed information. In fact, we sent both Voyager, well, if you want to go back to the beginning, Pioneer 10 and 11 both went by Jupiter.
Right.
Voyager 1 and 2 went by Jupiter and studied the moon as well as the planet. And we even put the Galileo spacecraft in orbit around Jupiter to get lots of detailed observations of the planets. And now we have Juno. And Juno's in orbit now around Jupiter making observations. So it's not like we've never been close to Europa to get very detailed images of a surface. In fact, I'll show you that on the next slide here in a second. But what this James Webb Space Telescope image is showing is the detection, because of the spectral type of observations you can do in the infrared, is that there is carbon coming off the surface in the form of the carbon dioxide. That actually points out to an ocean under the surface, which is mainly an ice and rocky surface, but probably mainly ice surface. Under the surface, then, is this liquid ocean. Liquid water is our best guess. And this is just another a piece of evidence in favor of these recent observations. Now, Robert, some people speculated, as I heard, I won't mention any names, that somehow the Hubble Space Telescope provided a much higher resolution image of Europa in the optical than what the James Webb Space Telescope can do in the infrared. Now, if you look at these two images, what you can clearly see, hopefully, that the image on the left is clearer, sharper, than the image on the right. They both resolve features, but the one on the left, the one taken by the James Webb Space Telescope, I would argue is of superior quality than the one on the right, taken with the Hubble Space Telescope of the same object. Now, there is a difference here, which limits the direct comparison of the two. The James Webb Space Telescope image is in the near infrared, where the Hubble image is in the optical light. Now, we know when you're looking at details of objects, there are two primary things that affect the resolution, as we say, the ability to see details.
Right.
Number one is the diameter or the size of the telescope. You think of the diameter of the lens if it's a refracting telescope, or the diameter of the mirror if it's a reflecting telescope. But the second one is the wavelength that you're observing at. For longer wavelengths, the resolution is poor for a given diameter telescope compared to shorter wavelengths. So with Hubble observing at a shorter wavelength on average than the James Webb Space Telescope, it is already set up to provide a higher resolution image.
Right.
But the James Webb Space Telescope is on the order of 6.5 or so meters in diameter.
Right.
The Hubble is about 2.4 meters in diameter. So the James Webb, from the point of view of just diameter, should provide a higher resolution image.
Yep.
And even the fact it's looking at a longer wavelength, which would degrade the resolution, that provide less detail, it still provides a better detailed map, I would argue, of the surface of Europa because of that huge increase in the diameter of the instrument compared to the Hubble.
The really telling point is how sharp are those lines between that delineate the features. And the one on the left definitely has sharper lines to it, like around that white region, than the hazy lines around regions on the Hubble.
Right. And just to kind of illustrate the difference in resolution, if you want to turn to the next slide, Robert, then what we see in this. That's going.
Yeah.
There,
there's the clipper.
This is the one. Okay.
That's the one.
Yeah, so on this slide, what you can see on the left is the highest resolution image that we have currently of the surface of Europa. So this was taken by the Galileo spacecraft from a distance of about 200 kilometers from the surface. And you can see the resolution information given there. It's each pixel on this image on the left represents, the size of each pixel represents 6 meters.
That's impressive. I didn't know it got that close.
Yeah. So that's kind of good. Now you might wonder, what's a meter? So 1 meter is about 3 feet, if you're using the imperial type of units here. And so that gives you an idea. So just multiply by 3, so 18 feet per pixel. So that's the resolution you're getting here. It's nearly 20 feet. And that shows you some remarkable detail. In fact, so remarkable, you can almost envision yourself walking on the surface of Europa very carefully, because you don't want to fall down any of those crevices that you see there.
Because it'd get mighty cold.
Yeah, exactly. And that ice is so cold, as we talked about. How cold is it? That's like a joke coming here.
How cold is it? The ice is like granite.
Yeah, it's like rock. It's so cold. There's no give to it, no deformability at all. So it's extremely rigid, extremely solid because of the very cold temperature that we find on locations in the outer solar system like this.
So how is there liquid water underneath there?
Yeah, so one of the things is, like Io, for example, if you we should have had an image of Io.
We should have had an image of Io, yeah.
But one of the big surprise when Voyager 1 went by the Jupiter system is when it photographed Io, they noticed the plume on the edge of Io. And that plume turned out to be a volcanic plume.
Yep.
So Io has volcanoes. In fact, it is the most active body in our solar system in terms of volcanisms.
Yeah.
And it almost looks like a pizza in some sense.
It does.
Right? Like a cheese pizza. And it's like the mainly sulfur material, molten sulfur that's inside of the interior of the moon Io that goes around Jupiter is being, put out onto the surface through this volcanic type of activity.
Yep.
And the heating, so you might say, well, there must be a tremendous amount of heat in the interior of Io. Why is that when it's out in the outer solar system? It's due to gravitational
heating. It's the tidal forces of its elliptical orbit around Jupiter, squeezing it and then letting it go and squeezing it. And, it's like taking a paper clip and folding it back and forth a few times, and you touch where it was folding, it's hot.
Yeah.
So it's the same type of thing. It's being compressed and then released several times over the course of its 1.8 day period.
Yeah, on that order. So so it's the tidal forces heating it up. The stretching and squeezing ever so slightly of the body, and that heats up to the point where you're going to get extremely volcanic activity that we see here. In fact, Europa would be the same thing.
Europa has the same issue going on.
Yeah, except it's not so extreme, that you're going to have, huge volcanoes on its surface, but it's enough to keep any water that's underneath the surface in the liquid form, right?
Right.
Water's liquid, but H2O, if you want to be more technical. We always use the term water, not referring only to liquid, but also in frozen water.
I will point out that you also have to be careful with the term ice, because, you get out to like Saturn and everything, and you start having ammonia ices and things like that. And, but in this case, we're talking about water ice. So
yeah. Now, Europa, you remember the significance of Europa in the movie 2001?
All of these worlds are yours except Europa.
Yeah, so that was Arthur C. Clarke. He separated Europa from the rest of the Galilean moons as a place where humans could go, but you weren't allowed to land on that moon.
Because they'd started life, the aliens had started life on Europa.
Now, when Arthur C. Clarke wrote that novel that ultimately led to the movie, this was long before we knew anything special about Europa. And it turns out that Europa is very interesting because we think there is a potential, a non-zero probability, be the way to describe it, that there may be life forms. Let's say swimming around in the subterranean ocean on Europa. It's warm enough that maybe biology might have occurred.
Right. It would be very akin to what we see around the black smokers and white smokers at the bottom of our oceans, near the mid-oceanic ridges.
Right, so we have these extremophiles, as we call them here on the Earth, where we have biological systems, life forms, that seem to be living around conditions that we wouldn't find hospitable, but they certainly do. In fact, they live off the ones that you mentioned, the geothermal activity. That's their energy source.
That's their energy source.
So they don't need the sun in that sense. They, they'd be doing just as well if there was no sun, as long as they didn't get frozen and couldn't move that way, right?
Right.
But if around the geothermal vents, of course, it would be melted, right? Any ice, it would have enough energy to do that, and they would survive in those vents.
In fact, around those vents, it's over the boiling point of water on the surface.
Right.
Down at the bottom of the ocean, the pressure is enough that it's not going to boil. But, it's if that water were on the surface, it'd boil away.
Right, so H2O is still in a liquid form then near these vents, even though they have a high temperature, well above the 100 degrees Celsius, the boiling point.
Right.
And that's standard atmospheric pressure,
Right. Not tons and tons of pressure.
Yeah, exactly. So Europa is one of these very interesting places where people often point to maybe biology, something is alive on Europa, either underground or somewhere. So in order to kind of lead down the natural road of exploration is to do follow-up missions, very detailed studies. So there was a push, actually a long time ago, several decades now, putting together what we call the Europa Clipper mission. So there are different incarnations of this. That is, you start off with a certain design, it gets turned down by NASA, then you go redesign it to find out why did they turn it down? Oh, it was too expensive, so let's shave some instruments off, let's redesign the mission to make it cheaper. And you go through this long process. It's not easy to, at the conception and take it all the way to launch, right? That's a long delay. That's why, scientists that spend their time like planetary scientists developing from the ground, developing these planetary missions and actually having them go, get launched, get to their objective, take the data, have the data come back to Earth, process or analyze that data and then publish the papers. That can be your whole career, just one mission.
Right. Some of the Voyager people, they were young, just getting started scientists when it was launched, and they were retiring about the time it made its last pass by Uranus and Neptune.
Neptune, yeah. And so, that's just the nature of the game right now. It's such a time. So to get Europa Clipper to the point where they're actually constructing it, which is the image that you see on the right, is some snapshots of Europa Clipper. And actually, if you want to watch it, don't do it now, of course, if you're listening to the podcast. And if you are, of course, please give us a thumbs up and subscribe if you haven't already. But you can just type in the search bar on YouTube, the Europa Clipper Live. And you can go to a JPL, the Jet Propulsion Laboratory site. There'll be a link that actually shows you the Europa Clipper in one of the clean rooms, and people are actively working on the instrument today.
Right.
So it's kind of cool. You can see it as it's being, put together, if you like, piece by piece and tested and so on.
Right.
And so this spacecraft is due to be launched in October of 2024. That's not too far away. It's about a year away from now.
Yeah.
And it's supposed to arrive at Europa in 2030, so 6 years to get there. It was not so bad.
That's not too bad.
Unless you're 95 years old or something, that may seem like that may as well be infinity, right?
Right.
In some sense, but it's all relative, as Einstein says, So, but for younger people, of course, 6 years is not that big of a deal. But in 2030, then, we're going to have a very powerful spacecraft in orbit around Europa doing very, very detailed observations of its surface. And that's going to be very exciting to see the information that comes back from this mission.
I'm looking forward to it.
I wish,
I'm like, wow.
I wish the sky, let's say, when you dream, you once said to me, Robert, you can dream, if you're going to dream, you may as well dream of everything. That's like last night when you gave a talk here.
May as well dream big.
May as well dream big. So if I had a dream, the dream would be that we don't waste all our money fighting each other.
Right.
And we don't need a military because you don't have to worry about anybody trying to take over our stuff, that kind of thing. And we could redirect some of this funds, not all of it, just some of it, into things like exploration and try to uncover all the mysteries that are out there. Who doesn't like to explore?
Right.
Seems like it's built into a human trait is to explore.
Yep.
Whether that's
except for a few people. There are a few people out there who I just don't understand that just are like, this won't benefit anybody, so why are we doing it? Well, stay home then, you homebody.
Well, that and by the way, the opinions that Robert and I
express
on this podcast is our own and not necessarily those of the university, the college, our department, and yada, yada, yada. Now, Robert,
Yeah.
it seems like the desire to explore, to see what's over the hill around you, is probably comes in at a level I could see, a million years ago, right? When we're hunters and gatherers, trying to go, going over the next ridge, looking for a supply of water and food and so on, right?
Right, looking for supplies and resources.
Yes,
Absolutely.
exactly. So it's in our inherent nature, it's built into us to want to explore.
Right.
And why not, to get to the nearest star to our sun, Proxima Centauri, which is 4.2 light years away. And if you don't know what a light year is, it's the distance that light travels in 1 year.
Right.
Okay? So
It's a distance.
It's a distance. We can get to the sun in a little over 8 minutes, traveling at the speed of light.
Right.
We can get to the outer solar system in several hours, traveling at the speed of light. To get to the nearest star to our sun, it's over 4 years.
Right.
So if you're traveling at a much slower speed, let's say
It's
the
even
fastest
longer.
spacecraft, you're talking tens of thousands of years to get to the nearest star. Okay, are we going to explore the nearest star? Yeah, eventually, if we don't kill each other, right? If
Right.
technology with the engineering a lot of engineering can be done in a couple thousand years. So, I have no doubt that eventually we'll get to the point where we'll have spacecraft that can travel, a appreciable size of the velocity of light, even
Right.
20%, 30%, 40%
I mean,
or whatever.
we
right?
can envision about 10% right now. With
Yeah.
the technology we have, we could probably get up to about 10%, pushing the limits.
Right. So at some point, we're gonna be able to travel fast enough, a large enough percent of the speed of light, that it's now worth doing
Right.
the journey to places like Proxima Centauri. Right. It's the old argument like Columbus would have made. Right. Oh, it might take me months to get across the ocean. I'm gonna wait until the 747 is invented. Then I'll go. You see? Well, if we all did that,
Right.
that would really hinder
Then
progress.
nothing would ever get done.
Yeah,
Right.
so at some point we're going to go on this journey. You just don't want to go now because 20 years after you've set off from Earth, here comes, future spacecraft zooming by you and you get there years and years before you will, right? So, yeah, so there's a point of diminishing returns. You don't want to go too early and
Right.
you don't want to go too late. So at some point we'll be able to do that, but we don't have to wait around for this technology to develop until we get up to 10 or 20 or 30% speed of light. We have this whole beautiful solar system surrounding us here.
Right.
And
let's learn about it first.
Yes, those objects are within years of reach, right, with present technology, right? They're not hundreds of years, centuries it takes to get there, or thousands of years. We can get there in a decade or so. So why not explore everything we see in our solar system that's interesting?
Oh, absolutely. Absolutely.
And this includes, Europa. In fact, imagine a mission that hovers around the rings of Saturn and explores all the material that these rings are made up of. You can think or envision all kinds of wonderful destinations within our own solar system that we would love to go to and explore, even by just robots.
Right.
So robots is the cheapest way to get there. You don't need the redundancy. You don't need to carry your own air. You don't have to carry food with you. Right? All of this kind of stuff. So it is a lot cheaper than to send robots. In fact, if something happens to the robot, yes, we may lose the mission, we may lose all of that money and investment of time, but we didn't cost anyone's life, you see?
Right.
So it's much better from that point of view to send robots. And if you can make them cheap enough, instead of sending one robot, let's send 10. If
Right.
one or two fail. We still have 9 or 8 of them left over to do the job. So we have a built-in redundancy, a natural thing. So I can envision, a time in the future where we'll be sending out what today we call CubeSats, these small little micro satellites
that
all
would
around
be
the Earth,
cool.
except they are probes to go look at various things in the solar system,
Yeah.
various destinations.
I like that idea. I've always liked the idea of CubeSats as long as they come back down in a relatively short amount of time. Do your job, come back.
Well, I mean,
burn
there's
up in
been-
the atmosphere.
Yeah, well, several groups have sent off these CubeSats to go explore the moon. There were some of them riding on board the launch of the SLS, the one launch we've had
Right.
up to this point, as sort of cargo, free cargo in the sense that they had extra ability to
extra
take
weight
up. Yeah, they could take up mass, right? Because they didn't have it loaded full of everything on board that rocket that they would do on a normal mission to the moon with
Yep.
people on board, manned mission. And so there are different ways to get up these CubeSats, and they're relatively small, so it's not that expensive, and so you can send up several. SpaceX, I think, have sent up lots of these things. In some sense, you could say that these Starlink satellites are CubeSats anyways. They're micro type of satellites compared to what we used to send up, like in the 1960s and 70s.
Right. They're a few tens of pounds instead of tons.
Yes, exactly. Yeah, so I can see that happening. And like I said, this is a natural progression. My only sort of negative feeling in all this is I wish I would have been born like 500 years from now to see how much we've explored in our solar system. Maybe we've started those first interstellar journeys. And of course, that's not going to happen in my lifetime, that we're going to send people off to the nearest star beyond our sun. But
maybe be one of those mythical creatures that can go take a nap for a few hundred years, then wake up and say, what's going on?
Yeah, the whole hibernation, right?
Yeah.
Or, of course, you could use relativity, the special theory of relativity, travel very fast relative to the Earth, right?
Right.
So time relative to the Earth has slowed down dramatically, so you might age several years, but back on Earth, maybe thousands of years have gone by, depending on the situation and how fast you're going relative to Earth. But if I had the technology to do that, then I'd have technology. Let's just redirect that ship towards Proxima Centauri, right?
Absolutely. I was going to say that, but you beat me to it. Yeah.
But anyways, so moving on from this news, there's also been very interesting news that's come out very recently, and this, as we always like to do, people speculate by various things, but until the research is published, that's what we're looking for in science, right? You get the credit for being first because you published, not because you had a press conference to say, hey, I think this is what I discovered. It's supposed to be through publication, because all of our science, then, at least it's supposed to be, peer-reviewed.
Peer-reviewed.
So other scientists, other experts in the field can look at what you've done to make sure you haven't made mistakes, that your conclusions that you have reached are consistent with the data that you have, that that are nonsensical or something like that.
And this is also,
sense.
though, why they're starting to require that you release your data with the paper. Well, so other people can go and analyze.
Yeah, well, part of that is that, and the other part of it is a lot of the data is collected through federal research dollars, and that federal research money comes from the people, and the people want to see what they're getting for their money.
Right.
So that data is technically not the scientists' data; it is the ones who supported financially the gathering and analysis of that data, and then it's that we, the people.
Right.
If it comes from the United States, right? So that's the big push on that, right? Is that data should be accessible to everybody.
Yeah. And in case you didn't know that, yes, you can go and request data from any of these studies. There's at most there's a small administrative fee that may be for calling up the disk that it's stored on.
Right. So this particular item that we're talking about, Robert, if you want to bring up the slide that shows the paper. So this is a paper that was recently accepted for publication. You can see the date, September 22nd, I believe, on the side on the left. Can you make that out?
September 23rd.
23rd. And this paper is based on what we call deriving the rotation curve of the Milky Way. And it's based on data from the Gaia space mission. Now, the Gaia mission is a mission that was launched by the Europeans to look at very careful measurements of both the positioning and motion of stars in our own Milky Way galaxy. Now, it does this by surveying large swaths of the sky. So along with that, you also observe other things beyond the Milky Way.
Yep.
Other galaxies and so on and so forth. But let's just focus, no pun intended, let's just focus then on the stars in our own galaxy. Okay? Mm-hmm. And from this data set, very careful analysis, very careful measurements, you can measure both the distances to these stars using the parallax technique. Now, this is the technique, just to remind you, or maybe you're tuning in for the first time here. This technique is what a surveyor would use, for example, to estimate the distance to some remote object. Let's say an object's on the other side of a large lake, and you want to try to estimate. This is the time before GPSs, of course, and having detailed maps to do this stuff nowadays. But you can do surveying, looking at what the object is relative to the background from two different vantage points. And by knowing what is the separation of your two observation points, and by measuring the angle of where the object appears to be, you can get, therefore, a measurement of the distance to the object from that center baseline. It's analogous to, for example, if you put your finger in front of your nose, and everybody who's listening now, please do that. Put one finger in front of your nose, certain distance away. Look at where your finger is relative to the background when you look at it with one eye. Then close that eye and use the other eye to look at your finger. And notice the shift in position. If you can do it, you can kind of go back and forth with your eyes. So that shift that you observe is related to two things: how far away the finger is from the end of your nose, from your eyes, essentially, and how far apart your eyes are spaced.
Yep.
Okay. That's what we call the baseline. So by observing the stars from different locations and measuring them very accurately on the sky, and these observations are done by the spacecraft that is in space, it's not affected by the Earth's atmosphere, then by observing them very carefully over periods of time, you can get an estimate then, you can measure that shift in position, you can get an estimate to the distance to the stars using this technique.
Absolutely. And that's what we've been doing for about 100, 150 years.
Wow, I'm glad you mentioned that. There's an interesting history here. In the early days, let's say very early days, back in ancient Greek times, we're talking like 2,000 years ago approximately, there was the dominating model that explained the universe, the geocentric model, the Earth-centered model, which said essentially the Earth was stationary and everything goes around the Earth, the sun, the moon, the stars. Okay?
Right.
Now, the contrasting model was the one that Aristarchus had mentioned. Somebody's mentioned Aristarchus had talked about this model in their writings, and that writing survived. The direct writings from Aristarchus never survived. So we have no record of what he actually said from himself, but first author type of information. But what he suggested was, no, things go around the Earth like the sun. The Earth rotates on its axis, the sun goes around the Earth. That can explain the movement of the sun in the sky over the course of the day and so on, and then the movement of the stars and the moon in the sky, those all go around the sun, and the Earth goes around the sun, right? So he suggested the alternate position, that instead of the Earth being the center of everything, it was the sun that was the center of everything, and the Earth goes around the sun, okay? That model was thrown away or wasn't accepted, so nobody really, pushed that model forward. Why? Because when you're standing on the surface of the Earth, do you feel the Earth moving, Robert?
No, but it's got a constant velocity, so I wouldn't expect to.
Well, people speculated that since the Earth doesn't, there's no motion, the Earth doesn't move. That's a natural, logical assumption that they made, right? I don't feel no motion, the Earth doesn't move. Now, when I'm out on a boat in the harbor floating around, fishing, right? When the boat moves, I can feel that motion. I can sense the motion. I'm moving. But where's the movement of the Earth when I'm standing on it?
Well, you feel the motion of the boat because the waves are moving it up and down constantly. Whereas if the boat was on still water and your eyes were closed, you wouldn't feel the motion of the boat.
See, there's the connection. Anytime that I'm moving, that I can actually see it, then I feel the motion. Right. That was what was assumed, you see?
Right.
Now, because of that, it was hard to get somebody to agree to the fact that the Earth's in motion around the sun, right? It's better, it seems more logical, and you look up in the sky in the day and in the evening, everything seems to go around an Earth that's not moving, it's at rest.
Right.
Okay? But the other opinion, that things go around the sun, that is not something that you feel naturally.
Right.
But if the Earth does move around the sun, and this idea, this model in some sense was reinvented by Copernicus in the 1500s, the heliocentric model of the solar system, if the Earth does orbit the sun, then that means at a given moment we're on one side of the sun in our orbit, 6 months later we're on the other side of our orbit. So if we look at the same star 6 months apart, we're seeing it from two different vantage points, and like the finger in front of the nose analogy, we should see that star shift position relative to the background of more distant stars. Yep. We should observe its parallax if that star is close enough, you see?
I was about to say.
Now, the astronomers back 2,000 years ago, they were as smart as we are today.
Right.
Just because, you were born 2,000 years ago don't mean you were stupid or whatever you want to say. You're less intelligent than people born today.
Right.
So they looked for the parallax of the stars. So if the Earth moves around the sun, that parallax should be observable. It was never seen.
It was never seen.
And so that was a negative against the heliocentric model. The model of Copernicus, the model of Aristarchus, was that you can't see the parallax shifting of the stars. Now, to be fair, they didn't know, for example, 2,000 years ago, that the stars had the distance that we know they have today, right? The average distance of the stars in our Milky Way are just so far away, those stars, there is no way you can see that shift in that, because the angle is so tiny, you need a telescope. So, people started using telescopes in the early 1600s.
Yep.
But even with the early telescopes, you couldn't see the shift. In fact, Galileo is reported to have looked for the shift in the position of one of the stars in the middle of the handle of the Big Dipper, Mizar and
Alcor.
And these stars are so close together, you can actually, with good vision, you can see there are two stars close together in the middle of the handle of the Big Dipper. So if you get a clear sky and you have decent eyesight or you have eyeglasses, look for that. It was used as an eye test for the military back in the days, right? And so what Galileo did was observe those stars with a telescope looking for the shift in position. He thought they were wide different distances, and so there'd be a near star and a far star, and we're on one side of the Earth of the orbit around the sun, and then observe it when we're on the other side 6 months later. You should see a relative shift in the position of those two stars. He never saw any.
Right.
Now Galileo was a supporter of the heliocentric, the sun-centered model, and this went against it. This should happen. I don't observe it. So, like a good scientist, he published. No, he didn't. Good scientists, even in negative results that don't abide by what you think should happen, right? Some experimental results, you publish that anyways because that might tell you your model A needs maybe to be modified, or B, maybe your model then is totally wrong. You need to throw it away and come up with something new. Galileo didn't do that. He hid those observations. He didn't publish them. He slid them in his drawer of his desk and filed them away, you see, and were later discovered by other people after he had passed away. That's not good, but cut him a break. This is the beginning of really modern science at the time of Galileo.
I was about to say, he's really one of the first. So
yeah. So anyways, the Gaia mission, using this parallax techniques, can make very accurate measurements of the distance to stars, and number two, by tracking their motion, it can actually see the motion of the stars, what we call proper motion in astronomy. Now remember, these stars are not stationary, even though they appear to be stationary to us. These stars are just so far away, we can't perceive that little small motion, but this spacecraft can. All of these stars are moving because they're in orbit around the Milky Way. So they're in constant motion, just like our own sun is in orbit around the Milky Way, and it's carrying all the planets with it, all the solar system with it. So with the data from this spacecraft, this very exceptional data, very precise data, we can track very precisely the orbital motion of stars in our own galaxy. And what they looked for was something that we call the rotation curve. Now, the rotation curve is a plot essentially of how fast stars are moving versus how far away they are from the center of the Milky Way. So, for example, when you look at the slide that you see in front of you, this is an older type slide that was produced that was supposed to illustrate the rotation curve on the Earth. What you see is the data, which is sort of the bluish curve that you see there. So notice that close to the galaxy, the center of our Milky Way, you're on the left side of the plot here. So distance is along the horizontal axis. That's measured in light years in this case. You can see the position of the sun with that arrow pointing downwards. Orbital speed, and the units here are kilometers per second, is plotted on the vertical axis. Okay. That blue curve illustrates the average of the speed of stars then in our galaxy as it relates to distance from the galaxy. So notice that if you were right at the center of the Milky Way, and by the way, you don't want to be there, why? Because there's a supermassive black hole at the center, but exclude that, assume it was nothing at the center of our galaxy, you're not going to be orbiting anything, so your orbital speed is going to be 0.
Right.
So you start off at the point 0, 0, okay? And as you get further and further away from the center of the galaxy, your speed will increase as more and more mass lies interior to your orbit.
Right.
That's the idea. So eventually what happens here in this curve is that the curve flattens out essentially. Yeah, there's bump and wiggles due to that our galaxy has a bar in it and so on and so forth. It's not a completely homogeneous or uniform disk. And so, but essentially the rotation curve is what we say flat. Okay. Now, when we get to the outskirts of the disk of our galaxy, all of the mass lies interior. There's really nothing beyond that. So you think that your orbital speed should decrease, just like the orbital speed of the planets decrease as you get further away from the sun. By far, the 99+% of the mass of our solar system is inside of our sun. So when you look at the orbital speed of Mercury and then look at Venus, Venus travels slower in its orbit in terms of its speed. Earth slower still because it's further away. Mars slower still, Jupiter, Saturn, Uranus, and Neptune. And so the further you are away on average from the sun, the slower you move in your orbit. That's known as following the laws of Kepler. So Kepler used positioning of planets like Mars from Tycho Brahe and derive his 3 laws of planetary motion, just to be sake of completeness here, Robert. First law, planets orbit the sun in ellipses with the sun at one focal point.
Right.
The second law says that the planets sweep out equal area in equal times, which just means when a planet is closer to the sun in its orbit, it moves faster. When it's furthest away from the sun, it moves the slowest in its orbit. And the third law, the period squared is proportional to the semi-major axis cubed. That just states that the greater the average distance a planet is from the sun, the slower it moves in its orbit. So it obeys the Keplerian type orbits. And if stars in our Milky Way on the outskirts obeyed the laws of Kepler, which we assume they should, because it's basically describing the influence of gravity,
right,
then the star should fall along that dash, sort of reddish line you see there that has a pointer to it that says Keplerian orbits. But it doesn't. It follows along the blue curve. So when you get to the outskirts, like 60,000 light years from the center of the Milky Way, the stars in our galaxy are traveling way too fast compared to what they should.
Right.
Now, this was a mystery at first when it was detected. And how we clear up this mystery is that we make an assumption that there's a lot more mass to our galaxy than in the form of stars, things that we can see.
Right.
And this eventually became known as dark matter. So one of the primary pieces of evidence for dark matter in our own galaxy is these flat rotation curves. So if you want to map out the extent of this dark matter in our galaxy, you try to map out as accurately as possible the orbital motion of these stars, especially those in the outskirts that are going to be influenced the most from this dark matter.
Right.
Okay? This was done with the Gaia mission. And this is the result from this paper then. And what we see here is a new, if you like, rotation curve made of the Milky Way using these exceptional data products that come from this mission. What we notice is, unlike the previous slide, the rotation curve is not flat out to the outskirts. Okay? Right. The rotation curve, as you can see in this plot then, tails downwards. So as we get to the outskirts, as we start to head out to the outer part of the disk of our galaxy, so if you look at the plot on the left, for example, we have the same kind of thing that's plotted here. We have speed in the same units as the previous slide, kilometers per second. But on the bottom, in the horizontal axis, notice the distance here from the center of our galaxy is in kpc. That stands for kiloparsecs, thousands of parsecs. Now, a parsec is a unit of distance. It's equal to 3.26 light years. So you can actually do the conversion from light years from the previous plot to kiloparsecs to what we're using here as a unit of length on the horizontal axis in this plot. Now, the interesting thing is there are a few different studies that have been done using different types of samples of stars from the Gaia data set. And they're all consistent with what you see here. Now, this particular study is the data symbols that are red in color on this plot on the left. And what you see is beyond a certain distance, you could argue, given the uncertainties, there are error bars attached, uncertainty bars, if you like, attached to data points, that beyond roughly around 19 kiloparsecs or so, there is a distinct trending downwards of the rotation curve.
Right.
Which tells us essentially we are on the edge of this dark matter halo. We've detected it. The rotation curve is no longer flat.
It's more Keplerian.
It's Keplerian at that point. In fact, you can then use models to determine how much of normal matter in the form of stars, let's say, whether it's gas, dust, or stars themselves, the so-called baryonic matter that we describe it as, that is protons, neutrons, these sort of things, compared to how much dark matter do you need to add into that mixture to reproduce the rotation curve that has been observed with data from this Gaia mission. And that's the plot that we see on the right side. So the top curve in this plot, once again, speed versus distance, is the black curve with the red data points superimposed. So the red data points are the observations along with the error bars, and the black curve then is the combination of different models, one that includes dark matter and one that includes normal matter. The normal matter is the blue curve that you see there, but the red dash curve is labeled there dark matter, as hopefully you can see. That's the contribution that you need in material that doesn't give off light, this mysterious dark matter that we don't know what it actually is, but we can detect its gravitational influence like what we see here in these rotation curves. In other words, if you use just normal matter in the form of dust, gas, or stars, you cannot reproduce that rotation curve. You cannot get those observations. It doesn't work.
Right.
If you add in dark matter to the normal matter, that red dash curve that you see there below the data points, and add the two together, you get that black curve that runs right through the observations. It is a good match to the actual data, to reality. So our model, which needs to include both normal matter and dark matter, fits the observations. Now, we could also fit the prior observations of the totally flat rotation curve. So what gives here? What has to change? What has to change is the amount of dark matter.
Right.
The amount of dark matter, instead of being approximately 6 times the amount of normal matter, is 3 times the amount of normal matter. You still need lots of dark matter to explain the rotation curve, but because it's no longer flat out to this, as far as you can measure now, we don't need as much dark matter.
Right.
But we never eliminated dark matter. It's like we never solved a so-called dark matter problem. We still need dark matter. We just don't need as much to explain the downward trend in the orbital speeds of stars in the outskirts of our galaxy.
And so we still need to figure out what the heck it is.
We still need to figure out what the dark matter is.
Yep. So, coming back to us.
So that was major, very nice observations showing a very good use of the Gaia mission, really showing you, with advancement of instrumentation to do better measurements in science, then some of these sort of issues that have been hanging on, whether it's the dark matter or dark energy, all these other major problems that we have to look at here in astronomy and astrophysics, that we can start resolving some of those issues to better understand where they come from. Is there really a problem like we think there is? Or maybe it's not as bad as what we thought.
Right.
And that's really interesting. So stay tuned. Keep watching these podcasts. You never know what type of observations or discoveries are made in astronomy.
If more comes up, we'll bring it up.
We'll bring it to you as soon as we can. Yep. So anyways, we're at the end of the podcast.
Yep.
So I want to thank everyone for watching. If you don't watch live, of course, thank you for watching.
Thank you for tuning in.
Yeah, thank you for watching our podcast no matter when you watch it. And if you enjoy this podcast and would like to see it live, we always do our podcast on Tuesdays at 3 p.m. Central Time. Mm-hmm. And so you can do the time adjustment wherever time zone that you live in. Now, if you're interested in science and physics, or even if you're not interested in science but want to do some education beyond the high school level, please feel free to come to the University of North Dakota. If you can, come on campus. Look Robert and I up. We'll be happy to chat with you.
Absolutely.
And if you can't make it here physically, you can also come here virtually, and that's by taking online courses here at UND. We have a very wide program of different courses that are available, and so you can then increase your knowledge. And remember, a day's wasted if you don't learn something new, Robert.
Absolutely. I will agree.
And so learning is one of these lifelong activities. Nobody said it has to end at high school. Once you're done learning. No. In fact, you're just beginning to learn at that point.
I agree. I absolutely agree.
Now, we always leave you with a quote at the end of the podcast. Today's quote is from somebody that only has one word for their name.
Oh, so Greek.
Yeah, Plato.
Plato, okay.
And here's a quote from Plato. Astronomy compels the soul to look upwards and leads us from this world to another. Thank you very much for listening, and we'll see you next time.
Thank you, folks. You have a good day.